So if nobody will join us today, so it will be only me and you and recorded materials. Then let's start. Okay, one person more. I will share the screen and then we will start to discuss advanced techniques in LLM deeply. So we will discuss today merge methods and we will deep into instruction tuning more than we did it previous. So we will dive into merge algorithm and instruction tuning. We will explore their technological foundations, also practical implementations, and ancient the adaptability, significance in ancient the adaptability and efficiency of modern large language models. Our discussion will cover the following topics: an introduction to merge algorithm, including their purpose and various types such as linear interpolation, spherical linear interpolation, ties, and there we worked with them on Tuesday when we had lesson with coding. So we will deep into them more, and also we will explore instruction tuning, its importance, underlying principles and process. Also, we will watch some examples like alpaca and vicuna. We will conclude by examining effects of instruction tuning and addressing each challenges and limitations. So what is merge algorithm? Merge algorithm are techniques used to combine two or more models into a single a unified model. This process leverages the strengths and knowledge of individual models to create a more compressive system capable of handling a broader range of tasks or improving performance on specific tasks. In machine learning, merging models can be viewed as a form of ensembling learning, where multiple models contribute to the final prediction. However, unlike traditional ensembles that maintain separate models, merge algorithms integrate the parameters or outputs of models to form a coherence unit. This integration can occur at various levels, such as combining model weights or blending outputs, and it's designed to enhance generalization, reduce overfitting, and improve robustness. So yeah, what is it? And you can see visualization of views of LLMs. For example, we have a lot of models. We did it on a lesson on Tuesday, so you kind of understand the intuition of this approach, but maybe visualization will show you that we have different important weights of different models, and every model is unique and can perform on different tasks. So we will fuse matrix or model with different important parts of every model that we have in the beginning. And in the result, we will have a strong model with great quality and strong capabilities. So the section is leading us to use this model on different tasks and on different areas. So with merging or fusing, we can achieve better results in specific projects on specific tasks. So let's discuss why we merge models. We talked about this a little bit, but let's talk in a deep areas of this. So merging models offers several advantages. It enables consolidation of knowledge from different models, facilitates the adaptation of pre-trained models to new tasks without extensive training, and can lead to improved performance through the integration of complementary strengths. The rationale behind merging models includes, firstly, resource efficiency. Combining models allow for the resource of existing models, reducing the need for training more new models from scratch and conserving computational resources. Also, when we merge models, merging enables the seamless transition of models to new tasks of or domain by integrating specialized knowledge from different models. And by integrating models with complementary strengths, the merged model can achieve better performance, as we as we said, than any individual model alone. So interpolation. Interpolation is, in the context of merge algorithms, refers to the process of combining the parameters or outputs of two models to create a new model that embodies characteristics of both. This technique is used to blend models in a controlled manner. Also, interpolation involves creating intermediate representations between models, allowing for a smooth transition from one model's behavior to another. And this process can be linear or not linear. And a crucial in scenarios where gradual adaptation is desired. Interpolation helps in balancing the influence of each model, ensuring that the merged model retains the strengths of both parent models while migrating potential weaknesses. So here you can see a graphic of interpolation that if it's linear interpolation, we just need to find point in the middle, and we will say that interpolation in the simple action works like we just find one point in the middle of our linear graphic, and it would be the result. So why interpolate between models? Interpolating between models allow for creating of a new model that balances the behavior and knowledge of original models. This technique is practically useful when aiming to combine models trained on different tasks or datasets. Interpolation serves several purposes. It enables a gradual shift from one model's behavior to another, which is beneficial in tasks requiring incremental adaptation. Also, by controlling the interpolation parameters, one can balance the contributions of each model, ensuring that the merged model doesn't overly favor one source, and interpolating between models can lead to better generalization across tasks or datasets, as the merged model encapsulates a broader range of knowledge. Here you can see some graphics of interpolation and their error quality on different different models, and also there is different environments. Let's move to linear interpolation, or in short, LERP. It combines two models by linearly blending their parameters, and you can see a formula here. So we will see that W, like it's a width of the model, parameters of two models, and T is the scalar between 0 and 1 that determines the blending ratio. LERP is a string-forward method for merging models, offering simplicity and ease of implementation. However, it may not always preserve the geometric relationships between the model's parameter spaces, potentially leading to suboptimal performance in complex scenarios. The linear nature of LERP assumes that the optimal path between two sets of parameters is a strength line, which may not hold true in the high-dimensional non-convex landscape, typically of neural networks. Here you can see graphics from paper. It's a combining of LERP and still LERP, which we'll cover on this slide. Spherical linear interpolation improves upon linear interpolation by interpolating along the shortest path of a hypersphere. This method preserves the geometric properties of the parameter space, leading to smoother transitions between models. Also, as LERP addresses the limitations of LERP by considering the curvature of the parameter space by interpolating along geodesic of the hypersphere. And LERP maintains the angular relationships between parameter vectors, resulting in more nature and coherent blending of model behaviors. This approach is particularly beneficial when dealing with models whose parameters lie on a manifold, as it respects the when it respects geometry of parameter space. And here is the visualization about all which I told on previous slide. This is when it's the case when we need shortest path of hypersphere. Let's talk about implementation of spherical linear interpolation. It involves several key steps to ensure a smooth and geometrically accurate transition between two model parameter sets. The process being with normalizing the parameter vectors of the two models to ensure they lie on the unit hypersphere. This normalization is crucial as LERP operates on the premise that the vectors are of unit length, facilitating interpolation along the shortest path of the sphere's surface. Once normalized, the angle between the two vectors is computed using the dot product, which provides the cosine of angle. And this angle determines the arc along which interpolation will occur. The interpolation itself is performed using formula with sinuses, but I don't see it's on the slide. There is formula with sinuses multiplied on width, and this formula ensures that the interpolation follows the geodesic path of hypersphere, resulting in smooth transition between the two sets of parameters. After interpolation, the resulting vector is generalized to match the original scale of the model parameters. This step is essential to maintain the appropriate magnitude of the parameters, ensuring that the merged model functions correctly. Implementing SLARP requires careful attention to numerical stability, especially when the angel is small. This can lead to deviations by values close to zero. In such cases, it's common to use linear interpolation as an approximation, given that for small angels, the linear path closely approximates the spherical path. Advantages of SLARP offer several significant advantages over linear interpolation methods. And firstly, it preserves the geometric relationships between parameter vectors by interpolating along the shortest path of the hypersphere. The preservation is crucial in maintaining the integrity of the model's learned representations, ensuring that the merged model retains nuanced behaviors of the original models. And secondly, SLARP provides smooth and continuous transitions between models, which is essential when blended models trained on different tasks or domains. This smoothness helps to avoid abrupt changes in model behavior, leading to more reliable and predictable performance. Additionally, SLARP allows for flexible merging strategies through the adjustment of interpolation parameter T. We remember it from the formula, and by varying T, one can control the degree to which each model contributes to merged models, enabling fine-tuning of the merged models characteristics to suit specific application. Okay, so let's move to ties. If you have no questions right now about previous methods.
No questions.
So this algorithm is designed to optimize the merging of models by addressing specific challenges that arise during the process. One of the primary challenges in model merging is the presence of redundant or conflicting parameters, which can lead to degraded performance in the merge model. Ties tackles this issue through a two-step process: trimming and sign election. In the trimming phase, the algorithm identifies and removes redundant parameters that do not significantly contribute to the model's performance. This eradication in parameter redundancy helps in streamlining the model, making it more efficient and less prone to overfitting. The sign election phase addresses the problem of conflicting parameters signs between models. When merging models parameters with opposite signs can cancel each other out, leading to a loss of valuable information. Ties resolves this by electing the dominant sign for each parameter, ensuring that the merge model retains the most impactful features from each original model. By focusing on the most influential bytes and resolving conflicts, ties enhances the overall performance and robustness of merged model. Here's visualization how TICE is working. TICE algorithm operates on the principles that not all parameters in neural network contribute equally to its performance. By identifying and retaining only the most influential parameters, TICE effectively reduce the complexity of merge models without sacrificing accuracy. These selective retentions aligns with concept of model pruning, where less important parameters are removed to improve efficiency. And additionally, the sign election mechanism is in TICE ensures that the merge model preserves the constructive interface of parameter contributions, thereby maintaining or even enhancing performance. This process approach is particularly beneficial in scenarios where models have been trained independently and may have developed different parameters signs due to random initialization or divergent training path. Let's talk about implementation algorithms. It involves several crucial steps by ensure effective model merging. To process begins with the identification of redundant parameters in each model. This identification is typically achieved through sensitivity analysis or by evaluating the contribution of each parameter to the model's output. Parameters this exhibit low sensitivity or minimal contribution are considered redundant and are candidates for trimming. Once redundant parameters are identified, they are removed from the models, resulting in a more streamlined set of parameters. The next step is alignment of parameter sign between the models. This alignment is crucial because parameters with conflicting sign can negate each other's effects when merge, leading to loss of important features. The TICE algorithm resolves this by electing the dominant sign for each parameters, ensuring that the merge model retains the most impactful characteristics of the original models. And after aligning the signs, the parameters from the two models are combined to form the merge model. This combination is done in a way that preserves the when the most influent parameters result in model that integrate the strengths of both original models. Like on the visualization, where in the beginning we thought that the most important parts of the models are combined in one. So optimization task of TICE method addresses two primary sources of interface when merging models, redundant parameters values, and site disagreements across models. To mitigate these issues, TICE introduces an optimization task that involves resetting parameters with minimal changes during the fine-tuning, resolving sign conflicts, and merging on the parameters aligned with the agreed upon sign. This process ensures that the merge model retains the most impactful features from each original model, thereby enhancing overall performance and robustness. The optimization task in TICE is designed to minimize the loss of valuable information during model merging by focusing on parameters that have undergone significant changes during fine-tuning, TICE effectively captures the essential adaptations made for specific tasks. Resolving sign conflicts ensures that the parameters contributions and constructive rather than canceling each other out, which is crucial for maintaining the integrity of the merge models functionality. This approach aligns with principles that transfer learning, where the goal is to adopt pertain models to new tasks while preserving previously accurate knowledge. And there are a lot of advantages of this method. The first one is reduced interface by addressing redundant parameters and sign conflict. TICE minimize destructive interference between models, leading to more coherent integration. Also, the selective merging process ensures that the only most impactful parameters are retrained, which can result in improved performance on downstream tasks. And this method is applicable across various modalities, domains, and model architectures, making it a versatile tool for combining multiple task-specific models into a single multitask model without additional training. Also, by carefully selection which parameters to merge, TICE helps in retaining the specialized knowledge each model has acquired, facilitating better generalization across tasks. Is it clear? Any questions?
That's good. Thank you.
Okay, let's talk about there. In my memory, we talked about this on this technique on lesson when we wrote code. So let's talk about this method more deeply, and also I will talk about implementation of this method too. So there is model merging technique that focuses on reducing redundant delta parameters. The difference between fine-tuning and pre-trained model parameters, it operates by randomly dropping a proportion of these delta parameters and rescaling the remaining ones to approximate the original model's output. This approach aims to minimize interference between models during merging, and thereby preserving the performance of the fine-tuned models in the merge outcome. This algorithm is grounded in the observation that fine-tuning often introduces sparse and redundant changes to model parameters. By selecting pruning these changes and appropriately rescaling the remaining parameters, they maintains the essential adaptations made during fine-tuning while reduces the risk of parameters conflicts. This structure aligns with the principles of model pruning and specification, which seek to ensure the model efficiency without compromising performance. Let's talk about formulas. Firstly, there is random dropping, a certain percentage of delta parameters, the difference between fine-tuning and pre-trained parameters. They are randomly reset to their original pre-trained values. On the second stage, the remaining delta parameters are scaled by a factor of this formula, where P is a proportion of parameters that were dropped. Looks a little bit like dropout. This rescaling ensures that expected value of models, outputs remain consistent with the fine-tuned models. And on the final step, merging, the adjusted delta parameters are then added to the pre-trained models parameters to form the merged model. Okay, their merging formula is designed to balance the retention of fine-tuned adaptations with the mitigation of potential interference during model merging by controlling the proportion of parameters that are dropped and appropriately rescaling the remaining ones. There ensures that the merge model maintains the performance characteristics of the fine-tuned model. This approach is useful in scenarios where multiple models fine-tuned on different tasks need to be combined without extensive retraining. There are 4 stages of implementation in this algorithm. On the first stage, when we compute delta parameter, for fine-tuned model, we calculate the delta parameters by subtracting the pre-trained models parameters from the fine-tuned models parameters. Then, as I told about like a dropout drop-in, we randomly select a proportion of delta parameters and reset from them to 0, effectively retrieving those parameters to their pre-trained values. It looks really like a dropout because we do the same operations and use the same idea, but in different way. And for the third stage of implementation, rescaling, we multiply the remaining delta parameters by this formula to maintain the expected output distribution. It's like a compensate of previous step. And on the merging parameters, we adjusted delta parameter back to the pre-trained models parameters to obtain the merge model. The implementation of there is based on principle that not all parameters changed during fine-tuning are equally important. By randomly dropping a subset delta parameters and rescaling the rest, there effectively reduces the complexity of the merge model while preserving its performance. This method aligns with concepts in stochastic pruning and parameter averaging, offering a practical approach to model merging without the need for extensive computational resources. There are some advantages. For example, by reducing the number of delta parameters, there simplifies the merging process and decreases the computational burden. Also, the rescaling step ensures that the merge model retains the performance characteristics of fine-tuned models even after parameter pruning. Also, it have flexibility in this method. Let's see the robustness of this method on graphics and in a scientific paper, which is linked here. Okay, we will talk next about pass-through. In my opinion, it's a very simple method, which it's simple to use. This method are also known as it has a second name, and sometimes it involves creating a composite model by integrating components from multiple pre-trained models without modifying their internal parameters. This approach allows for the combination of specialized capabilities from different models and the single framework. enabling the model to perform a variety of tasks by routing inputs of the appropriate submodels. The primary advantages of the pass-through method is its ability to leverage the strengths of individual models without the need for extensive retraining of parameter adjustment. However, this technique requires careful management of the interactions between the integrated components to ensure coherent overall behavior. The pass-through approach aligns the concept of mixture of experts, and it was released and on the top when mixture of experts was on the hype about half year ago, maybe 1 year, I don't really remember in these time breaks. So we explored mixture of experts and let's understand why it's really close to the idea of a mixture of experts. Okay, it's a mixture of experts. Different experts are responsible for different tasks of data domains. By direct inputs of most appropriate expert, the model can efficiently handle a diverse set of tasks, and this method is capitalize on the specialized training of each component model, allowing the high performance across various applications. However, to create and multiply models in this manner can introduce challenges related to model model complexity of managing multiply components within a single system. And ensuring the combined model operates seamlessly requires careful design to coordination among the integrated parts. So in this case, we have a lot of how to explain this. If we will just merge different layers to each other, we will go for the really it looks like a way when we have a lot of experts but we have a lot of experts here to ensure amount of our parameters and models, make it bigger to follow scaling laws that we explored on the first lecture of large language models, or on the second one. So, but here we also change our amount of our parameters of the model, but not with going not with stacking experts in the same time, which are working like on the one line. We stack more layers on like in a line, and it works because we create our model deeper, bigger, and it can perform better with this taking more layers. Just so there are about 5 stages of implementing this method. First one is select from component models, and define and select pre-trained models that processes the specialized capabilities required for the target tasks. Second one, it develop framework that allows these models to operate in correct way, ensuring that the inputs are correctly routed to the appropriate model based on the task of data characteristics. Then we establish a mechanism to direct each input of the corresponding submodel. This can be achieved through predefined rules or a gating network that dynamically assigns it's based on their features. Then, last but not least, we combine the outputs from the various submodels into unified responses. This may involve selecting the output from the active submodel or integrating outputs from multiple models, depending on the application's requirements. And on the last stage, we ensure that the integrated model maintains consistent behavior across different tasks, addressing any discrepancies that may arise from independent training of the component models. There are a lot of advantages of this method. By integrating pre-trained models without altering their internal parameters, the path-through approach retains the specialized knowledge and capabilities of each component model. This method aligns the need to extensive pre-train, saving computational resources and time. Also, the modular nature of path-through method allows for easier updates and expansions. New models can be integrated into the system to accommodate additional tasks for domain without disrupting existing functions. Also, by leveraging the strengths of specialized models, the path-through approach can achieve high performance across a diverse set of tasks, and as each submodel operates within the area of expertise. So, area of expertise. Let's talk also about challenges and limitations in this approach. The first one, you can see that there are huge top of this challenges and limitations. So, firstly, merging models trained on different tasks can lead to interference where the performance on individual task degrades due to conflicting parameters updates. Also, combining multiply models can result in a substantial increase in number of parameters, leading to higher computational memory requirements. Also, we have it in mixture of experts in training an algorithm. In the process of merging, the unique strengths of individual models may be diluted, resulting in merged models that lacks the specialized capabilities of its predecessors, and ensuring complexity in integration between models with different architectures of or training paradigms can be complex and may require sophisticated alignment techniques. Also, merging models trained on sensitive and or proprietary data can raise privacy issues, especially in merged model exposes information from the original datasets. If there are any questions about merging, because we will move now to instruction tuning. Okay, so instruction tuning is crucial because it bridges the gap between models' pre-trained capabilities and its ability to follow specific human instructions. By fine-tuning models on datasets that pair instructions with desired outputs, we enhance their responsiveness and adaptability to user directives. This process not only improves performance on practical tasks, but also enables model to generalize their understanding of instruction, making them more versatile and effective in real-world applications. And the significance of instruction tuning files in its ability to align large language models with human intentions. Pre-trained models are typically optimized for next word predictions, which doesn't necessarily equate to following human instructions. Instruction tuning addresses this mismatch by training models on instruction output pairs, thereby teaching them to interpret and execute tasks independent by users. This alignment is essential for deploying large language models in practical scenarios where understanding the human instructions are paramount. Let's talk. We talked a little bit why this important, because we need to show the model how to communicate in that way that human need. In this case, when you communicate with chatbot, you can text their instructions. For example, answer me in that style. Please tell me in this way. Maybe if you had something in the context, in this case of instruction tuning, you can tell them reformulate this all this text in another way that I need. And because of this, we can do it easily. Yeah, here is some visualization how instruction tuning is working. And let's talk about principles. Ensuring that models understand and execute tasks intended by users. Also, training models to apply learned instructions to a variety of tasks, ensuring their versatility, and also utilizing a wide range of instructional prompts, corresponding outputs to cover different scenarios and instructions. Continuously updating and fine-tuning models based on feedback to improve their performance and enhance to instructions. These principles are foundational of development to large language models can effectively follow human instructions. By aligning models with human intentions, we ensure that their outputs are relevant and useful. Generalization across tasks allows model to apply their understanding to new and diverse challenges. Data diversity ensures that models are exposed to a broad spectrum of instruction, which is crucial for robust performance. Iterative refinement enables continuous improvement, allowing models to adapt to evolving user needs and expectations. Let's talk about process. It's kind of 5 stages of the process, and first one is that set collection, gathering a data set of instructional prompts paired with desired outputs. Then we pre-process it, cleaning and formatting the data to ensure consistency and capability with the model's input requirements. Then we train the model on the prepared dataset, adjusting its parameters to minimize the difference between its output and the desired responses. Then we evaluate the model's performance on validation set to ensure it correctly interprets and follows instructions. And on the final stage, we refine the model based on evaluating results, which may involve additional training or data augmentation to address identified weaknesses. Here is kind of visualization of the process. The structured approach ensures that the large language models are not only trained on vast amounts of data, but also specifically tuned on understand and execute human instructions. By following this process, models become more adept at handling a wide range of tasks and directly used by users, thereby increasing their practically utility. And there is a first example. It's Alpaca is an example of model fine-tuned using instruction tuning techniques developed by researchers at Stanford University. Alpaca was trained on a data set of 22,000 instructions responses, pairs generated using OpenAI API, GPT model. This fine-tuned process enabled Alpaca to perform a variety of tasks by following natural language instructions, demonstrating the effectiveness of instruction tuning and ancient model capabilities. The development of Alpaca illustrate the practical application of instruction tuning by leveraging a large data set of instruction response pairs. The model was able to learn how to interpret and respond to a wide range of directives. This approach showcases how instruction tuning can be used to adapt trained models to perform specific tasks more effectively, highlighting its potential and creating AI systems. The second case is Vicuna is another model that that trained from instruction tuning, fine-tuned on user shared conversations from platform like shared GPT. Vicuna was trained to generate more human-like and engine responses. This fine-tuning process improved its ability to follow complex instructions, to engage its multi-turn dialogues, making it more effective in conversational AI applications. Vicuna development underscores the importance of high quality, diverse data sets and instruction tuning. By training on real-world conversational data, the model was able to learn the nuances of human dialogue, enabling it to generate more natural and contextuality appropriate responses. This example highlights how instruction tuning can be tailored to specific applications such as conversational agents to enhance their performance and user engagement. So we'll talk about agents on the next lesson. Instruction tuning. Okay, we finish this topic by effects of instruction tuning, and then we will talk about challenges of this method. Firstly, improved task performance. Models become more proficient and executing tasks as specified by human instructions. Also, models can employ learned instructions to new and seen tasks, demonstrating flexibility and adaptability. Also, models produce outputs that are more aligned with user expectations, increasing their practical utility. And models become more resilient to complex instructions, maintaining performance across diverse scenarios. And the last slide about challenges and limitations. Firstly, research indicates that instruction tuning doesn't consistently improve a model's knowledge or skills. For instance, models like LoRa may only train models on response indentation and style, while full parameter fine-tuning can lead to knowledge degradation. Also, replicating response patterns from instruction datasets sourced from entities can result in diminished response quality, and particularly if the model relies on these patterns without educate contextual understanding. Full parameter fine-tuning may elevate the likelihood of hallucinations, where the model inaccurately borrows tokens from contextually similar increases in the instruction dataset to generate responses. Common techniques aim to improve the instruction tuning do not always lead to performance gains over simple models fine-tuning with adapters. Also, models fine-tuned on specific instructions may struggle to apply their knowledge to new or unforeseen tasks, limiting their versatility. So there are a lot of risks, like or fit to patterns in the instruction data, reducing their ability to think creatively or generate original responses. But it's like a base of alignment right now, and it really works. Also, if you will combine instruction tuning with chain of thoughts, like for example, in OpenAI model O1, they trained this model on chain of thoughts and follow instructions. So in this case, it helps a lot. And also, all challenges and limitations just signal us that we need to be really careful to clean our datasets and duplicate all stuff. Really clearly, and have a lot of attention that we don't need any garbage in the data. Also, it's necessary to have experience, like assessors with a lot of experience and a lot of knowledges in their sphere. So in this case, all will be good, and but yeah, it's necessary to remember that if we will do instruction tuning on bad pre-trained model, we will not achieve the results. So I think that we covered all the topics about in large language models advanced techniques. We covered on the previous lesson mixture of expert and BEFT methods. Today we explored merging algorithms and instruction tuning. All these algorithms is crucial on SFT part of alignment. We explored a little bit reinforcement learning, but we didn't deep there a lot, because I think you will have or had a particular course with reinforcement learning, and yeah, I think we are finished. So do you have a lot of do you have questions for me about any topics that we covered?
Was this the last lecture?
You will have another one recorded, and Radoslav will send this lecture, I think on weekends, or maybe In the beginning of next week, it will be about retrieval augmented generation and agent systems and large language models. It's also like a part, but of using large language models, but not in the pre-training or alignment stage. It's like techniques on like engineering techniques, and these techniques are useful on projects when you create systems with large language models. And yeah, and we will have I think the last lesson on Tuesday. We will code retrieval augmented pipeline and agent systems.
Okay, got it.
Thank you for your question. Maybe some other topics to discover or to communicate in which topics to. What do you want?
I think we also have 2 more homeworks, right?
I don't know. No, I know that in the beginning we thought that it would be 5 homeworks. I think in the beginning of next week, Radoslav will send me fourth homework about PEFT methods, and then I will post it in the Telegram chat. But maybe we will not have fifth homework because we will not have more time. Yeah, that's it.
Got it. Thank you.
You're welcome. Okay, so thank you for your attention. Have a good evening and good weekends. Goodbye. See you on Tuesday.